Thank you so much. Well, hi everyone. My name is Sara, and I'm going to talk about the warp drive, exploring the science fiction and reality of space travel. So, yeah, we will start. And in this talk, I will tell you a little bit about the connection of science fiction with reality, with science. How can we actually explain some of the most important concepts of science fiction, which is space travel and how to travel at the speed of light. We can see it in like Star Trek and all of these science fiction movies. There's always this concept about space travel and traveling at the speed of light. So I thought it was super interesting, and I wanted to make this connection and this bridge among these two. And I'm gonna tell you a little bit about one physicist that he made a metric, he made a mathematical model about this traveling at the speed of light without violating the general relativity, which is fascinating. So this is what we are going to explore right now. And I think history is pretty important, so I will give you a little bit of context and about, we will start from the beginning and we will speed up and go higher up in the skies, and we will tell you a little bit about this topic so you can fully understand. So I think going into 0 meters on Earth level, you know, ancient civilizations, they've always wondered about what's beyond us, what is in the skies. The Aztecs, the Egyptians, all of the ancient civilizations, they always ask about what's beyond what we can see and what is beyond, what is in the nature, what is in the stars, what is even a star. So this curiosity has always been part of humankind. And then if we look a little bit further in time, then we can see that space travel has been something that we will always want to pursue. And a lot of people doesn't know, but hot air balloons were one of the first travels or transportations that humankind used to explore the universe. So here we are locating a little bit about 22,000 meters from the Earth, that is going around the stratosphere. So with hot air balloons, with a helium-based system, we reached the stratosphere for the first time with hot air balloons. So these were like the first spaceships, as if you can see it like that, to explore the universe and to explore what's beyond the sky. And the velocities, it's a little bit about 5 meters per second. And this, for example, the Explorer 2nd, which was the one who first reached the stratosphere, was the round trip was about 80 minutes, so on. So another important thing was in 1957, the Sputnik 1, which was the first satellite that it was made by a human who was sent to space. It only lasted like 3 months until it burned out. And yeah, it reached 900 kilometers above the Earth, and it had a velocity, a speed about 28,000 kilometers per hour, which is a lot compared with the hot air balloons. And yes, this represented a huge thing for humankind, because then it was the first time that we were like, okay, now we can actually send something to space. We weren't that able to bring it back, but it was the first step for humankind to space travel. And then the same year, they sent Laika, that I think everyone knows about, this special dog. They sent her to space, and it was the first creature in space. So this was also a very, very important path in space travel or space exploration, because of course we are sending creatures to space because we want to send humans there. So we need to first see if it's safe for us, and then we can actually send a human. So this mission lasted about 5 months. Unfortunately, we couldn't bring her back either. But then the space race between the Soviet Union and the United States began. And of course, 1 year later, after Sputnik number 1, NASA was created. So of course they wanted to also send something to space. They were working on it, and they did with Explorer 1. again 1 year after, in 1958, all of these innovations were going very, very, very fast because, again, it was a space race. So with Explorer 1, it lasted around 12 years, which was much larger than the last one with the Soviet Union. It reached about 2,500 kilometers, and the speed was pretty similar to Laika's spaceship. And then, again, the United States didn't want to be behind it, so they sent another creatures to explore the universe, which was Abel and Baker. There's these monkeys, and this is very important because this mission was able to bring them back alive, and everything was fine with them. And this is super important because they, of course, explored first the flight and that they were safe and all of the math and so on, but also that it didn't affect them biologically, or that they didn't have any like secondary effects on them. So they could see that they were perfectly fine. So they were like, okay, now we are ready to send humans to space. So in 1961, they did. The Soviet Union sent the famous Yuri Gagarin, who was the first man in space. And yeah, a little bit about the altitude and the speed that he had. It was around the other spaceships that they were sent to space. His trip lasted around 2 hours. And then the United States also did send a man, which was Alan Shepard. It was the first man from the United States. And you can see a little bit about the comparison. What's interesting of this second trip was that he was able to manipulate himself, the spaceship. Yuri Gagarin, it was fully controlled by Earth, so he was not doing much in the spaceship. I mean, he was like not controlling anything about the spaceship. Everything was controlled on Earth, but Alan Shepard did control a little bit about his spaceship for a brief periods of time, not like the whole thing. And then, of course, the space race continue, and we had a lot of innovations. We had a lot of technology. The first woman was into space. The first man to orbit the Earth happened. The first satellite, or the first rover to go to the moon, was sent. And a lot of missions, like the Luna mission, the Vostok missions, the Apollo missions began because everyone wanted to reach the moon now. Okay, now we took a man into stratosphere. Now we take the man into space and back. Now we want to reach the moon. And so they did in 1969. That mission took 4 days. And the speed that they had, it was again pretty similar with the last missions that they had with Neil Armstrong and Buzz Aldrin, that I think most of us know about them. So the next step for humankind and for the space race was Mars. Now we have reached the moon. Now we wanted to go to Mars, which we right now we know that we have been there, or like that we have sent rovers. And NASA, they have this project, the Viking project, which is very interesting because they have sent some projectiles to Mars to collect rocks and some dust, and they are studying the biology from that, the atmosphere of that planet, because of course one of the main questions that we have is, can we go to Mars and live there and establish there to make like a planet to live in? And of course, under that search, scientists in 2017, I also wanted to include this one because I think it's also very important. We have that they found 7 Earth-sized planets with kind of the same atmosphere. They are pretty similar to Earth. And one of them is this one, Kepler, which is 300 light years away from us. And it's also important because it's part of the reasons that we explore the universe, because we want to see if there's any other types of life, or if we can go there and make our civilization and take humankind there. So for you might wonder, but why do we even explore the universe? Well, first of all, out of curiosity. Again, it's something that the human has always have inside them. They always had this urge to know what is beyond them, what is in the skies, and we don't know limits. So first, out of space, then the moon, then Mars, and then so on and so on. So of course, the curiosity to get to know the world around us. And of course, fundamental questions like what's beyond that, how big is the universe, does it have any time limit, what is there, is there any other types of life, and so on. And of course, with all of these questions, there's a lot of innovation that comes with it. So all of our smartphones, all of our the healthcare, most of the healthcare systems and technology that we have is thanks to space travel missions that they of course take them for planet for space exploration first, but then they can see that they can apply it on other type of things like healthcare, technology, universities, and so on. So of course that also brings us in culture, and inspiration is also very important because, well, there's this study that mentions that when Apollo 11 ended, there was like a race in the alumni numbers or the curricula in universities all around the world. So when people knew that we reached the moon, everyone was like, damn, I want to do that. And then they went and studied physics, and they studied STEM careers, and they wanted to pursue this scientific. So that's also very important for us because that brings us a lot of, that brings us together and we can collaborate. That was also the first time that in science we could see collaborations, because science back then was a little bit like nations separated, and space exploration was like such a huge thing, and there were such huge challenges that nations had to come together to collaborate and do partnerships to actually solve these problems together. And again, basically is to answer fundamental questions. So now we will go with the main topic of this talk, which is science fiction. So we know most of the people who are here are scientists. We know that science, it wants to discover and understand what's around us through a systematic way, through experiments that we now call the scientific method. However, the science fiction explores the possibilities that science can bring us, or even creates new questions that then science can look into. So for example, flying like a bird, or communicate kilometers away, exploring the universe. All of these things kind of started in science fiction, in movies, in films, in comics, and then science came, and now we can see that we have planes, that we have telephones, and all of these things kind of ended and started with an idea, and most of those ideas started in science fiction. So this is to create, to put you in perspective of the relationship between science fiction and science. One can inspire the other one, and vice versa. So just to give you a little bit of an example about this, for example, there was Japan. They sent a satellite. There was the Hayabusa one, and they sent it, and they were very proud of it, but no one really knew about it, no one really cared about it, and then the media made a movie about it, and it became so popular that then everyone knew about this mission, and everyone was curious about this. So this is an example that it was like science, and then in collaboration with science fiction, then you can create a connection with the public, that they can also be informed of that, because that's also one of the final goals of science fiction, to communicate a concept and to create awareness of what's going on in the scientific world. And also, I think all of this, you might know it. So Christopher Nolan with Interstellar, that is one of the basic movies that all physicists must watch, I guess. Christopher Nolan, his team went to some scientists, and they were like, we want to put some black holes in there, but we wanted to make it real. And then they create these simulations And then they came with this image in the left. And then in 2019, a few years later, then we had the first image of a black hole, which is this one. And you can see it's pretty similar. So that's the power of science fiction if you make it right and if you dig into that. So this is just to illustrate how both of them can inspire with each other. I will turn the volume up so you can hear this.
4.8. Point 9.
Well, this is just a very, very famous scene that I think most of us has watched, and that it represents so much to science fiction culture. This idea that now we are going to go to Star Trek universe, and the 5th of April of 2063, Shepard Cochrane, he did the first space mission to interact with the Vulcanians, that we all know them, I guess. And they used a new technology in the movie and in the universe, that it was the idea of the warp drive. So the warp drive is something that we're going to focus right now. And when they make this movie, well, this series, they of course wanted to make space explorations, and they wanted to travel at the speed of light and so on. But then when they looked at physics, they were like, oh, well, they encounter a few issues. The first one, space is very big, way, 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 way bigger than they thought. And into this, of course, general relativity, you cannot travel at the speed of light. So they didn't want it to violate those laws and those theories, but they thought it was not that complex to travel at the speed of light, and to even if they wanted to travel to the closest star, it would take so many years. And if they follow those rules, of course the whole show would be about everything happened on the spaceship, and without no action, no meeting new planets, no meeting new civilization, and etc. So they encountered this issue that they needed to overlook a little bit of the impossibilities of the physics, such as general relativity, to make this show possible, because then the whole show would be on a spaceship, travel from one star to the other one. And this is boring, so people want action, people want to see planets and civilizations and so on. So this was one of the first issues that they had. And I'm gonna read this. So what is this, the warp drive? It is warping space-time like the folds in clothes, bending reality somewhat to allow for travel faster than light. And they did that with a mechanism that it was taking annihilating matter and antimatter, and they will fusion it together, and then they would create an enormous amount of power. Of course, they knew that they needed so much energy to power and to propel all of these spaceships. And so this was their mechanism to do that. But if you read this quote, you might not really understand what's going on. What is warping? What is space-time? What does it mean to fold like clothes? What does clothes have to do with space travel and so on? But don't worry, we will go through some of the steps and some of the concepts to understand this better. So, yeah, first of all, the warp drive, is it even possible? So, well, an important fact about me is that I am from Mexico, and when I entered the world of physics, someone told me about this man, and I was like so impressed of what he did, and I really didn't understood his theory because I was like very, very young, and I didn't know anything like strong of physics to really understand what he was talking about. But basically, he is Miguel Alcubierre. He's a theorist, physicist, a Mexican who created a solution that is called Miguel Alcubierre's metric in 1994 to make Star Trek warp drive possible. So he literally was one time in his couch. This is a real story that he told us in one conference. He was doing his PhD in Wales, and he was watching Star Trek, and then he was like, oh wait, now I have the tools to actually understand all of this with general relativity and this and that and cosmology. And then he started to question if he could create a metric, to like a mathematical form to actually explain this, and he did. So what are we going to see today, which is a bit more the physics part, the hard part, is Miguel Alcubierre's metric. And to do that, we need a lot of general relativity that most of you might not have had before. So we will go step by step with some of the main concepts to fully understand the Alcubierre's metric. So the first one is space. So basically, very roughly, space is three-dimensional, where you can move in, again, 3 dimensions, and where all physical phenomena happens, where any object can exist and move. So this is very roughly what space is. Again, from now on, we will use light years as our measure of distance. Some people might think that light years is like velocity maybe, or some other type of measure, but it is not. So just basically light year is the distance that the light travels in a year, which is this one right here. But how big is space really? So for example, the distance from the Earth to the Sun is around 1.5 to the 10 to the minus 5 light years compared. And then the last planet of the solar system, it's like 5 to the 10 to the minus 4 light years approximately. But then if we go further up, the closest star to the Earth is 4 light years away from us. And the closest, the distance from our solar system to the inner part of our galaxy is around 26,000 light years. So just to put you in a perspective how big the universe is. And I chose this image because I think it exemplifies it very well. Andromeda is the closest galaxy that we have from us, which is around 2.2 million light years away from us. So, and this is only taking the closest things around us. Imagine what's beyond that, right? So, time. With time, I would like to put this table, I guess, to, I don't know if you could hear in the video, we had some technical issues, but they were like warp 1, warp 2, warp 3, and so on. And in the Star Trek, they use this as a measure of the speed. So they use warp factors. And if you take whatever warp factor and you take it to the power of 3, then that is the multiple of the light speed. So for example, if you take 6 warp factor, if you're traveling at a warp factor of 6, then you are actually traveling at 6 to the power of 3 speed of light. And for example, how much energy would it take to propel a spaceship to, let's say, 90% the speed of light? And we can see it here. This is a calculation that I did for only 1 kilogram traveling at 90% the speed of light, and it's about 1 to the 17 joules, which is like 50 megaton. It's a lot of energy that it comes a lot of technical issues with this, how to store it, how to get it, how to produce it, but we will not get into that. If we look at this formula, we can see that if we get closer to the speed of light, that v becomes closer and closer and closer to c, and we can visualize that that would represent an issue if it gets very, very close. If it's equal to c, then 1 minus 1, and that creates that will get us to have infinite energy and infinite mass. But now we will go into this concept that is time dilation, that might be a little bit tricky for this is one of the hardest things in general relativity, I will say. It's not very hard, math is not very hard, but it's kind of weird to really understand how to apply it into the reality, because you in special relativity, all of the calculations doesn't really depend of the observer. You know, it's inertial frameworks. But in general relativity, you really need to have on mind all of the observers, and that everything is relative, as they say, basically. So this is a formula for time dilatation. So we know about this clock paradox and so on. So basically, time dilatation, it's a phenomena that occurs when you travel at very, very high speeds. And the faster you move through space, then the slower you will move through time. This is the basic concept. And what happens now if we travel at 100% the speed of light? Then again, if we look at this formula, if we take v to close to c, because that means 100% the speed of light, then this would goes to infinite, and then we will be on the need of having infinite energy and infinite mass, and a lot of issues that comes with this, and also time's frozen, because then you wouldn't give it any time to travel from one point to the other one. You do it instantly. So time's frozen, and we will be in the need of infinite energy. So yeah, GR, general relativity. Again, you might not know that it was formulated by Albert Einstein, and basically it is a theory of gravity, where nothing, we know that in spatial relativity, nothing can travel faster than the speed of light. However, in general relativity, we can do that, and we can kind of shape that behavior if we look at the local space. So if we take a very, very small region of space-time, we can actually take it as it is flat. So that what locally means. Take a small region of space-time, and then you can take it as if it's flat, and that makes all of the calculations much easier. You know that physicists, we like to go to the simplest case ever, and this is one. And this is the equation. Then again, you can also put there if you take the speed of light at 100 and so on. So last concepts to fully understand Alcubierre's metric is space-time, metric, and the expansion of the universe. So we now have seen a little bit what is space and how big is space, and a little bit about time. But we know that in general relativity, one big concept is space-time. So it is a four-dimensional continuum that you take your space coordinates that we know is 3, and we know that time has 1 coordinate, but special relativity and space-time fusion this together sees them as a single entity. So space-time is a four-dimensional continuum where the coordinates can be expressed as this form, time, and then the coordinates of space that you can move around it, basically. Now we will look at another very important thing, that is the metric. Again, in very broad words, the metric is the mathematical tool to explore and to describe the shape of the universe, the shape of space-time. And it literally, what it does, it takes a distance coordinate and it takes it into a physical distance. So you know how to, if we take, for example, a two-dimensional surface. We know how to construct a two-dimensional surface, which is with this equation right there. If we want to take the distance of this of one point to another one of this two-dimensional surface, then we will have this this formula right here. And if we do a lot of calculations, then we will arrive to the metric. So the shape of this space-time would be this one right here, that we will not go into many details. I just want you to kind of be familiar with the shapes of the metric. Now, if we go to the three-dimensional part, then again, it's the same logic. We know how to create a surface, that it's right there. And then, again, we take the distance from one point to another one, and then we will have the metric, which is that right there. And the last one is the four-dimensional, that is mostly known as the Frederick Robertson Walker metric, which is explained by this equation. So you can kind of see how all of these equations looks like, so you can understand what Alcubierre's metric is about. So last one is the expansion of the universe. Again, it's not only worth knowing that space is very, very, very big, but also that it's expanding. And we know this because, well, we know that it's expanding at a certain rate, which is Hubble constant, at a Hubble constant. And we know this because the galaxies are moving away from each other. This is not really true. It's not that the galaxies are actually like constantly going away from each other, but the space between them is increasing. So now we will go into Alcubierre's metric, which if we don't consider, if we are only in general relativity framework and we do not consider wormholes situations, then by purely local expansion, now we know what local means, of space-time, now we also know what space-time is. Behind the spaceship, an opposite contraction in front of it, motion faster than the speed of light, as seen by the observers. Outside the disturbed region, it is possible. Sarah, I still don't understand. Okay, don't worry. There's two main things that you need to know about this. The first one is that you need to expand the space-time behind you, and to contract it in front of you. So let's imagine I am a spaceship, then instead of me moving, then I will take space-time and then contract it in front of me and expand it behind me. Such as this image, the spaceship would be in the middle. And this might be a little bit weird to know it, so I will ask Christian to help me to do a little bit of a demonstration to visualize this better. So we know, let's assume this is a space-time grid and this is a spaceship. So from general relativity, we know that if we want to travel, if we want the spaceship to travel, then, well, let's assume that I'm not inclining it, but the spaceship will do that to get to, let's say, point A, which is me, to point A, which is Christian, to point B, which is me. And you can see that it's curving space-time. We all have seen this type of demonstration. But what Alcubierre really means is we take it from the half. Yep. So we want to take a spaceship from point A to point B without moving the spaceship. So we will put it there, and what he says is that I'm going to contract space-time, and he's going to expand it. And then you can see that at one point I will contract space-time so much in front of the spaceship and expand it so much there that the spaceship didn't move, but it still reached point B. So this is basically the idea of moving, thank you so much, of moving a spaceship from one point to another one without moving the spaceship, but moving space-time itself, which is amazing. Yeah, so what the question that Miguel did make himself to when he was thinking about Star Trek was, what would the metric look like for space-time that can contract and expand? So his idea was amazing. You don't have to move the spaceship. You need to control space-time itself. And he actually did with this metric, which it looks a little bit like this. Again, we have some of the coordinates or the components of the common metrics that we have seen before, but then in this formula, in that function, we can control this thickness of the bubble. They see it as this, as if it was a bubble where you contract and it's expand behind it and contract it in front of it. So you can control the thickness and how long the bubble is. So basically, this is the mathematical form to make space travel at the speed of light without moving a spaceship, without also violating general relativity laws. And why doesn't it violate general relativity laws? It is very simple, because the spaceship, it is not moving. So as simpler as that. You don't move the spaceship, so it's not really traveling at the speed of light, but you are moving space-time itself. That makes it go to one point to another one at the speed of light. So yeah, but of course nothing is that simple. In his calculations, he encountered one tiny detail that you need negative energy or negative mass, which we know in physics that, if we explore one of the two options, negative energy or negative mass, we know that negative mass, it is not possible. Physicists have proven that this is not an option to explore. We have never seen it. We have never theorized it. Yeah, you know what I mean. But the option of negative energy, it is an open question for physicists. So, well, the first point on the current situation is that we still do not have the technology to store or to generate that amount of energy. So that is the first point. The second one, negative mass, is out of the table, but the negative energy, it is still a possibility if you look into the exotic matter of dark matter. So if we somehow manage to work with one of these, then we will be able to take the energy to propel all of these theories. And you can do that with the Casimir effect. That you might want to look into that if you are interested in these topics. That is, they use the exotic matter in the theories. As conclusions from my behalf is that curiosity has always been part of humankind, that has taken us far, far away to reach the sky and beyond. That science fiction and science are very, very highly related, and that one can inspire each other. And that Alcubierre, he basically showed, he mathematically showed that it is possible to take a concept from Star Trek, such as the warp drive, and to make it possible without violating their laws of physics, which is amazing. And again, with his metric, hyper-fast interstellar travel, it is still a possibility, and scientists are still looking into that. And I think that's everything from me. Thank you so much.